Hello all. I'm going to do notes for you, with you, on a new subject, which is population ecology. So this is the key for that. So, a population. A population consists of all organisms of a particular species in a given area. Okay? Just one species. If you're talking about more than one, then it'd be community. Population ecology is interested in the characteristics of the population, factors affecting population size and density, and describing population growth when it's increasing, stabilization when the population's about the same for a while, and decline. Okay, demographics. Demographics of a population. Population size is the total number of individuals, which we denote the variable being n, the number of individuals. And remember, this is the number of one species in a certain area, or volume if it's something like fish. Population density. The number of individuals per area or a volume of habitat. So density would equal n over A if it's volume. If it's area. And if it's volume, like for fish, it'd be n over v. We have three tools, methods we use to determine population size. One is the quadrat method. And this works when you have very slow-moving or immobile organisms. So, for instance, trees, those would be immobile. Something like slugs, they're slow enough that when you do this, they won't have moved much when you do it. And that's this one over there. And here you stake multiple random squares. And they're literally squares that are a meter on a side. Okay? And you put down one of these squares that's hollow in the middle. You just flop it down, and you just walk around and flop it down randomly in different places within the area you're interested in. Why do that instead of just counting everything in this whole area? Well, what if it's like 1,000 acres? You're not going to count every tree in 1,000 acres. No, you're going to just sample part of it. And since it's random, when you add them all up together of your sample, it'll be a pretty good estimation of what it is for the whole area. Okay? So that's the quadrat method. By the way, quadrat are these little squares we're talking about. What if you have things that move around? Well, that would be the mark and recapture, and that's that one. And there you would capture a bat or a wolf or whatever. You put a collar or a tag on it, you let it go, and it moves around, and within the same area that you captured before, you capture whatever is there. Now, since things that move around, some of them will have a tag, and that's the one you caught the first time. Others won't have a tag, those are the ones that have come into that area. Okay? So that's this part here. So you capture them, you tag them, new, and you determine the ratio between the tagged or marked ones and the ones that were unmarked, and that'll give you some idea of what the population is for a much bigger area. It's very handy for animals that move around a lot. Even better that we have these days is electronic tracking, where things like commercial fishing, wolves, again, fishing, wildlife management, that sort of thing. This is like, it's sort of like mark and recapture, but it's a lot more precise than taking snapshots. We can see what's going on at any one time. And when I say snapshot, what I'm saying with mark and recapture, if you only do the mark and recapture once a year, that's kind of like taking pictures instead of like taking a movie with electronic tracking. Okay? So two different ways of sampling. And notice I'm saying sampling because we're not counting them all, we're just counting some of them and using that to project what the whole population is like. Now, when we've done these kind of measurements, we found that populations tend to distribute in three basic ways. One is you find the population evenly spread out. We call that uniform. And that would be this one, right? Evenly spaced. When does that happen? Well, that happens when there's competition, competitive interactions between individuals in the population over scarce environmental resources. So they spread out. Like water in a desert. Or it could be, if it's a rookery for penguins, it could be space to have a nest and defend that territory, and so forth. Which actually is the second thing, territorial. And that's often animals, where the animals are defending the territory, where they defend it against like other males if they want to have access to the females there. It could be over the food that's available in that space, and other things that that they want all for themselves. Another thing, and this kind of tells you plants, we think animals are so much better, but plants have their own fighting that they do. So a lot of them will secrete poisons that inhibit the growth of nearby individuals, often of other species. In their leaves or roots, like azaleas, black walnuts, elderberry. Those are just a few of many different species of plants that fight to have exclusive right to a territory. Okay, so the next sort of distribution is the random distribution. It's completely unpredictable. And this is often the case for organisms that are distributed by wind or water currents. So, for instance, dandelions or other kinds of plants that rely upon the wind to disperse their seeds. Or in the ocean, on water currents, where fish and other animals rely on water currents to disperse the eggs after they've been fertilized. The last sort of distribution is called clumped. And here individuals aggregate into patterns or patches. Several reasons for that. Could be plants that are dropping seeds straight onto the ground. So you may have heard the apple not falling far from the tree. That kind of that's an old saying that kind of gives you the idea. Well, it used to be, like a son being a lot like their father. But that's because in these plants, they just drop the seeds around them. So you often have clumps of trees of the same kind growing in the same area. That's pretty common. Great example of that are sequoias and coastal redwoods, where you have what are called groves of the same tree. A grove is just a clumped pattern of dispersion. Animals that live in groups for protection, usually from predators. Or mating behaviors. Schools of fish, herds of elephants, you get the idea. Another reason why you might see that is where only certain environments are suitable. Coming back to water, along streams, you'll often see cottonwoods that need a lot more water than other plants, say like ponderosa, which can tolerate much drier conditions. So let's flip over the sheet and look at some more examples. Okay. So patterns of population growth. There's different ways in which populations can grow. The simplest is exponential growth, where populations grow without environmental constraints. So this looks like a J that you can see over here. See, it looks like it goes slowly and then it just shoots upward. And that's because of doubling, 2, 4, 8, 16th, and so forth. You'll only see that where there are unlimited resources and kind of another way of saying that is no competition. Okay, you don't see that in the real world very much, or at least not for very long. What's a lot more realistic is what's called logistic growth. And that's population growth with environmental constraints. So that tends to look sort of like an S on its side. So you take the S and kind of turn it. That's what you see. And there are limited resources. There's a lot of competition for those limited resources. And those resources are denoted by what's called K. The carrying capacity that's how many organisms are supported by that environment. All right, so let's look at some examples of those. Leave that there for now. So here, these are paramecium that are in elaborate culture, and this is over a couple of weeks. You can see down there. So at first, it looks like it goes straight up. There are no constraints, but as the population gets closer and closer to the carrying capacity, and they're competing heavily for the resources, that it flattens out, and we see that's a logistic sort of a curve. Again, here we've got Daphnia. These are little, often called, what are they called? Oh, I forget. But anyway, these are tiny little crustaceans that live in the water. They're about 1 millimeter long. And the same thing, you start off with near zero, they shoot up. And the dots are the actual population, where the population overshoots. It's too much. There's too many Daphnia for resources. It goes below, and then it evens out in this smoothed logistic curve. This is actually not too uncommon. And here, fur seals on St. Paul's Island in Alaska. There, again, the dots are the real data, but it closely follows the logistic curve. There is limiting resources for breeding beaches where they breed and for the fish that they eat. Okay, so what limits populations then? What affects the density? Well, density-dependent factors are one, and those are population size affects its growth rate, and that could be competition for breeding grounds or for food or things like that. It could be how many predators are preying on the population. If you have a lot of coyotes eating up rabbits, that's going to keep the population of rabbits in check. Parasitism. When population density is high, it's easy for parasites to hop from host to host, and again, that's going to keep down the population. Same for disease. There's also density-independent factors. Population size has no effect on the growth rate. So unusual weather. If there's a hurricane and it wipes out a lot of trees, well, that's not because the trees were close together. It's because the weather came along and knocked a bunch of them out. Natural disasters, human activities. If you're clear cutting, hey, there's nothing that the trees can do about that, right? So if we look at three of these, this first one, that's exponential growth, right? It's just that J curve we were looking at. Logistic curve. Growth. That is density-dependent factors. So these up here will give you this kind of a curve, right? Density-dependent looks like this. Density-independent. You also get a logistic curve with density-independent, but it tends to look like a mess because generally density-independent factors are really unpredictable. Hurricanes, droughts, plagues of mosquitoes, stuff like that. All right, wow, moving right along. All right, so one last thing to look at are survivorship curves. And this is going to bring up one last idea for you. You know that a tree can produce lots and lots of seeds. In the fall, when all the seeds come down from my maple trees and I have to rake them all up, I can really see that. Each tree produces thousands of seeds. But are there room for all those thousands of seeds to turn into seedlings and fill up the space around the trees? Well, no, there isn't. Most of them will perish. But the maple tree makes thousands of those on the off chance that one of those seeds will find a space that is free for it to grow, to turn into adult, and make more progeny of its own. So those kind of organisms that make lots and lots and lots of young, in order to ensure that at least some of them will grow up to adults, we call those R-selected species. They produce lots and lots of offspring but provide little or no care. Among animals, one of my favorite examples are oysters. Oysters can live for decades. A female oyster can produce up to 1 billion eggs. Well, obviously, they're not going to all grow to be adults. Most of them, those eggs, when they hatch, well, the eggs themselves are food, and when they hatch into little juveniles, most of them will get eaten. Just a few will make it to adult oysters. On the flip side are those animals and plants that invest a lot of resources into the young, and we call those K-selected. They produce very few offspring, but provide them with good care. Okay? Our selected species tend to look a bit like this, where you start off with tons and tons of them. They don't make it very far through their young ages, and you get just a few of them as adults. On the other one, the ones that are very K-selected, moms and dads will only have a few children, but they tend to survive to adulthood and even into old age. Thank you, and I hope you enjoy assignment number 3, which comes right after this. Take care and goodbye.